Hello and good afternoon. This is a final project for CS465 for spring of 2025. Group members are Grace Haslam, Dylan Hun, Maya Swarup, and Wesley Umstead. VR is becoming more and more common in today's world, and we can see it starting to be used with its initial implementation was gaming, but now it's reaching out into other fields such as education, medical simulations, remote collaborations. We'll see companies using this for the education purposes for training, and it's becoming a cost-effective way to train people. For us, we wanted to consider a user who navigates a simple path in virtual reality environment. The experience may seem straightforward, but subtle differences in interaction techniques such as pressing direction buttons or tilting a joystick can alter how the task feels. Is this user, or is this task straining the user mentally? What does a button do? Is there thumb fatigue from repetitive pressing? Does the joystick offer smoother controls that feel more natural? These nuances in interface design can ultimately affect user satisfaction, efficiency, and even long-term engagement. In this study, we investigate how the interaction technique influences the perceived workload in a virtual reality task. Specifically, we compare 3 input modalities: joysticks, buttons, and hand gestures, by analyzing user responses to a navigation task implemented in Unity on a MetaQuest 3. We had 5 basic research questions that we set out to answer. Does the type of input modality, joystick versus button-based controls versus hand gestures, significantly affect a user's perceived workload when performing navigation tasks in a virtual reality environment? Question 2, when dimensions of workload are measured by the NASA TLX, temporal demand, effort, frustration are most affected by the choice of the input modality. Question 3, how does prior familiarity with gaming or virtual reality hardware influence perceived workload across different input modalities? Question 4, can joystick-based navigation in virtual reality reduce perceived frustration or improve task performance time compared to navigation with a button-based control or hand gesture control? Question 5, to what extent can the NASA TLX result from virtual tasks be used as reliable indicators of real-world usability challenges in multi-module virtual reality interface design? We see related works that we used to gauge what we were doing, and we see that in some virtual reality-based surgical planning and training, where they, in this specific one on the surgical planning, they use different interfaces to interact with the thing by doing, or different, excuse me, they use different devices to interact with while performing a surgery. We're also a study of Xbox controller as far as ergonomics and versus a gamepad. The study of hand gestures versus a gamepad interface, and the difference, and gamepad versus a keyboard. Effects of virtual reality on workload. Measuring the workload of input modalities in a virtual reality raises the question on how extended reality effects workload compared to a 2D application. Studies on the effects of presence, immersion, and flow in virtual reality found that the virtual reality simulations resulted in a lower perceived workload, but did not have any measurable effect on performance. Our study investigates the workload of specific input modalities in virtual reality navigation, where understanding perception and spatial reasoning can introduce new workload considerations. Sandra G. Hart's research on the NASA TLX provides an extensive insight into how workload is measured across different human computing interactions, which also includes virtual reality environments. The NASA TLX has been widely used in various fields, including aviation, remote vehicle operations, to assess the mental and physical workload differences between interface designs. This is a brief list of our participants. We'll go in more into this in the next slide. But just given a little bit of their user experiences, whether or not they ever used VR before or were an avid video game player, just some general information there. The participants we selected, a total of 8 participants on a volunteer basis to ensure ethical compliance and informed consent. All individuals were at least 18 years of age at the time of enrollment, with the average age of the participants being 26. The participant pool had an almost even split of gender, with 5 female participants and 3 male participants. The participant pool consisted of individuals with a varying degree of prior experience using virtual reality technology and playing video games. The diversity in experience will allow for a more comprehensive assessment of the user interaction experience. The apparatus used using Unity, we developed software to deliver the virtual reality experience. The software composed of 4 separate scenes. Each scene contains the same objective conveyed to the users by text on the screen. The user control a boat that they need to navigate across a simple path to the end of a stream. For hardware, a MetaQuest 3 will be used. This includes the virtual reality headset and the controllers. The controllers have a joystick and 2 buttons on each. We will use a computer to mirror the virtual reality content so that we can monitor the user interaction and activity. Procedure: the participants will be given instructions audibly and visually describing the controls they will be using to navigate the 4 different scenes. The description will be given before they put the headset on so that they can get an understanding of the controls before using them. Throughout the use of the virtual reality headset, users will be remain seated. Design: the independent variable is the input method used to interact with the content. We chose to test 3 input methods for this, which were the usage of the joystick, the buttons, or hand gestures. The buttons represent 4 discrete movement choices to move the boat, whereas the joystick allows for a continuous 360-degree movement. The independent variables is the perceived cognitive workload as measured by the NASA TLX load index. The NASA task load index questionnaire will be administered after each input method is completed. Despite our controlled methodology, several threats to the validity must be acknowledged, particularly in the context of immersion or of immersive virtual reality, which is prone to unique ergonomic and cognitive effects. One key concern is the potential for carryover and fatigue effects due to the within subjects due to the subjects within subjects design. All participants performed all tasks, which could introduce order effects, especially since virtual reality tasks can lead to visual strain, postural discomfort, and muscle fatigue during repeated trials. In addition, cyber sickness can be a form of motion sickness, which is unique to virtual reality environments and may emerge over time after participants' perception and behavior. This condition is often triggered by mismatches between visual input and vestibular feedback and can distort performance even in low motion tasks. We tried to keep the actual process of the demo short in order to minimize these potential side effects. Although the NASA TLX is widely used to assess subjective workload, it may not fully capture the complex interplay of mental overload, visual strain, and physical discomfort that virtual reality can induce. Figure 1 show the average raw workload scores per modality, with the joystick being in blue, the buttons in red, and the gestures in yellow. There seemed to be a far more fluid and smooth curve when it came to the joystick, and initially, it seemed to be the most efficient for the users. External validity, the generalization of our findings is limited by both the small sample size and the demographic uniformity of the participants. Research shows that cognitive fatigue and VR-related symptoms, for example, cyber sickness, vary based on age, gender, neurodiversity, and prior experience. Our sample composed primarily of university students that may not reflect a broader user population, particularly those in professional or clinical virtual reality applications. Because of our sample size was small, the statistical power, our results, is limited. According to Ackerman, some small sample sizes increase the likelihood of type 2 error, failing to detect real effects when they exist. This means subtle yet meaningful differences between the joystick and button input methods may have gone unnoticed due to a lack of sensitivity in our analysis. Figure 2 shows the standard deviation of scores per modality, and Figure 3, the average workload score by participant. Another interesting thing about Figure 3 is that, of course, the two individuals that had prior, or not necessarily prior, but used virtual reality on a regular basis, their workload for the gestures was scored lower than the others. We used a modified NASA TLX raw scale to measure the perceived cognitive workload of the users. We collected data on a scale of 1 to 7 from the participants in categories of mental demand, temporal demand, effort, and frustration. On average, the users reported that the joystick had the least perceived cognitive workload, closely followed by the buttons, as seen in Figure 1. Hand gestures had a significantly higher perceived cognitive workload than the other two input methods. The two users that had previously used virtual reality devices extensively had substantial lower NASA TLX raw scores for hand gestures, as seen in Figure 3. This suggests that prior usage of virtual reality on a regular basis could be correlated with a lower cognitive workload when interacting in a virtual reality using hand gestures. This could be due to the learning curve associated with getting used to the hand gestures in virtual reality. This aligns with prior studies on how the novelty of virtual action interactions perceived workload. The standard deviation for hand gestures was high across all dimensions as seen in Figure 2, showing that participants had varying levels of perceived workloads. While this study provides valuable insights into perceived workload differences between interacting using hands, joystick, and buttons in virtual reality, several limitations must be acknowledged. The reliance on the NASA TLX load index introduces potential subjectivity in data. Our study was conducted in a controlled environment, which may reduce ecological validity, while virtual reality allows for precise replication of experimental control. The contextual and emotional nuances of real-world use are often difficult to simulate. Our sample size was limited to 8 participants, which is sufficient for initial evaluation, but limits the generalization of the results. Our evaluation captures only post-task workload. Real-time physiological data such as heart rate, facial expression, or posture could provide deeper insights into moment-to-moment cognitive and emotional responses, but were outside the scope of this study. Future work could be done with a larger participant pool to find a stronger correlation between previous virtual reality and video game exposure and the cognitive workload of hand gesture control in virtual reality. Future studies could also focus on seeing if the correlation with cognitive workload differs when participants have only video game experience versus only virtual reality exposure, or versus having both experiences. In this study, we compared the cognitive workload of 3 different input modalities in virtual reality: joystick, buttons, and hand gestures. We did so by developing a prototype of a simple task in virtual reality using MetaQuest 3. This prototype was tested by 8 volunteer participants who represented their perceived cognitive workload using the raw NASA TLX. We found that hand gestures had the highest cognitive workload on average. However, the hand gestures also had the most variability depending on how familiar a user was with video gaming and virtual reality based on previous exposure. The work done by each group member have broke down into checkpoints and homework. The homework one. Homework 1, Dylan and Grace did the final implementation that was turned in. Wesley and Maya experienced difficulties getting Unity set up and working on MetaQuest 3. All groups had some sort of rudimentary versions of Homework 1 that we had on our personal machines. The version that had the most progress was then polished and used for submission. Checkpoint 1, we were in a bit of a rush as our initial proposal was turned down and we had to change it up. Once we got a new plan of attack, we divided up and decided who would do what. Grace and Wesley wrote the script for the video submission, as well as each recording a portion of it. We did not have much code at this point, as we were starting from scratch. Maya and Dylan were tasked with adapting the work to LaTeX, and they divided up sections, introductions, related work, and methodology. Maya put together the README and the PDF of the paper progress. Checkpoint 2, we kept with the responsibilities that we did on Checkpoint 1. Maya and Dylan did the vast majority of latex. Wesley added some sources and some content to related work. Unfortunately, a lot of the other content Wesley did was not able to be utilized. Grace took the lead on the Unity, with team members adding support when needed. Grace will also be doing, or also did, the video going over the code, and Wesley gave the progress update. For the final submission, Maya and Dylan finished up the latex, and Grace handled running the demo. Wesley got the remaining sources for Maya and Dylan. Grace covered the coding video, and Wesley was responsible for the final presentation video. This concludes our presentation. Thanks for a great semester, and we learned a lot, and we had fun doing it. Thanks a lot.